In AI, it's really something where like in three to 6 months, you can really learn a lot about how these systems work. It's not so complex. And I think it's probably worth learning if you think it's plausible that these systems are going to become that powerful, because I think we need our best and brightest to kind of, I don't know, have their game face on or something for the challenges and the opportunities that the technology might bring.
When I had like my personal runway, I ran out. And so I was like, okay, I think that I'm going to need 6 months of stealth study to have a shot at getting a job. At that point, it was DeepMind or Google Brain were the two places to do work there. Or Miri. Miri was the third one that I was looking at. So I was like, if I want to help out with that, those are the three places to look at. I don't have any of the skills yet. I need 6 months of self-study to feel like I would not be a drag on them and like actually be helping instead.
Can you maybe explain a bit what was that self-study like? Because I'm sure there's a lot of software engineers right now in their 20s that are looking to your tool to become AI researchers. What was that 6 months like? Even though, as you said, you had gotten a B- in linear algebra, which is like core.
Might have been a C+. I'm not. I should check. I'm going to give dollars.
That's pretty impressive where you got to.
Yeah, it turned out okay. First, I did a contract actually with Twitch, and like earned like enough to have that 6 months of runway. Okay. So I did like 3-month contract with Twitch, and then I made a plan to self-study. I don't think it's the right plan now for people too, at least in 2015. What did it look like? It was like take a Coursera course on machine learning, try to solve some Kaggle projects, read linear algebra done right. And I had a statistics textbook. I think I had YC alumni credits. And so I bought like a GPU and I would like SSH into the GPU to like work through my courses for it.
And this is right after, it was already after AlexNet, right?
It was after AlexNet, yeah. So I was mostly doing image classification stuff that I was trying to learn. It was like the thing that all the courses would teach you to do.
How did you get the OpenAI job? Because you were one of the few engineers who was mostly researchers, and they had a pretty stacked team of researchers.
I messaged Greg as soon as OpenAI was announced, and I was like, I'd love to help out in some way. I got a B- in my linear algebra, but I know some engineering. I've done a bit of distributed systems work. If you guys need help, I'm like happy to mop floors if you guys need. I want to help out, however.
Of parameters. And so I think this is another reason why this is a natural place for physicists to lend a hand, because these algorithms, quote unquote, are very different from ordinary algorithms that computer scientists study and prove theorems about. They're much more statistical as algorithms. Okay, so now I've just described some very basic way of constructing functions when your data is a high-dimensional vector, and this is what we use. The next question that we have to answer is, what's the goal of learning? So I'm going to break ML down into basically 3 questions. One is sort of how you define a function on the data. The second question is, what is the goal of learning? And this is actually the subset of ML that I think you can say the most about theoretically. However, at the end of the day, the things that you end up saying are very intuitive and kind of obvious. But this is the kind of thing that statisticians have studied for a long time, and so there's a lot of theoretical machinery you can talk about. Now, what is the kind of thing that you do? I told you that ML is just curve fitting. We now have this function. So something that I'm sure everyone has done is solve least squares. So we can write something called a loss function, which depends on our data and the neural network parameters theta. And so the simplest loss function is literally for regression, where the output of our neural network is not something even as complicated as which digit we have written in MNIST, but is just some real number y. And if our data is sort of x's comma y's, this is our data, then we can write a loss function L, which is, say, the sum over all of the data points of yi minus f theta of xi squared. So if we literally have regression, we're learning y as a function of x, then this is the kind of loss function you've probably just encountered. It's a very natural thing to write, and it's a loss function because big values of loss are bad, small values of loss are good, and so you just want to minimize this, and you're minimizing it, so we want to minimize with respect to the theta. So yi and xi are data, they're fixed, they're things that you actually have, they're facts about the world, and you're going to try to minimize this as a function of the neural network parameters theta. So this is the simplest possible example of what a loss function might be, and it just specifies a goal for learning. Now, in a lot of cases, you want to do something more interesting than just compute y as a function of x. For example, maybe you want a function that outputs which digit I've written. Is this a 4 or is this a 9? It's possible I have really, really bad handwriting and that this is a 9, but probably it's a 4. Yeah.
Sorry, quick question. The smaller the loss is, the better is the fit, correct?
Correct, yeah. Yeah. So it's called a loss because you want to make the loss small. I just convention that in the field they usually want to talk about minimizing something instead of maximizing something. Yeah.
One question.
Yeah.
So, I mean, does this have to do with overfitting and underfitting? How do you determine that?
Great. So that's a good question. I'm going to talk about it in a few minutes. Right now, I'm just ignoring it. This is something that you should absolutely ask about and worry about, and it's something that's surprising. There are surprising aspects of that in machine learning. So I'll talk about it in a few minutes. But if I don't, remind me. So sometimes you want to do something more complicated. I said that this is probably a 4, and when I say probably, you could then linguistically note that there's a notion of probability. In other words, I at least think about the world as when I look at the world and I sort of try to ascertain something, ultimately I think I'm making sort of probabilistic judgments. In other words, I say that this is a 1 and this is a 2 because I'm very, very confident. I have a very, very high probability for these being 1s and 2s, and a very low probability for them being any other digit, although of course there are some situations where I'm not really sure. So a natural thing our neural networks might output instead of a number like y as a function of x is a probability given x. So in other words, a natural thing to do when trying to classify whether I'm looking at a 0, 1, 2, 3, 4, etc., is I can have a neural network that outputs probabilities. And how do I do that? Well, in the simplest way, I can have my neural network output. I can first output, say, 10 real numbers. And then the second step can be, given 10 real numbers, there's an easy way of making those 10 real numbers into a probability, which is I can compute e to the xi divided by the sum on j of e to the xj. And this I can call my probability pi. So here I is, say, 0, 1, 9. And then I can, my pi is the probability that, say, what the image I'm looking at is one of the digits from 0 to 9. So this is sort of a very simple thing you can do to the end result of your neural network. You have your neural network first output 10 real numbers. This is called a softmax function in the literature. So if you see the word softmax, I mean, this is also just basically what you would do would have a Boltzmann distribution. But this is the terminology. I can learn these probabilities, and then I need to figure out what is my loss function if my output is a set of probabilities. If it's just a real number, then I can do this kind of naive curve fitting. But if my output is instead of set of probabilities, a thing I can do is I can do maximum likelihood. So what do I mean by maximum likelihood? Well, if my data consists of these digits as images, along with a label which says which image they actually are, then I just want to maximize the probability. I just want to maximize the probability of the correct label and minimize the probabilities of the other label, right? A good image classifier will say with 99% accuracy this is a 1, with 99% accuracy this is a 2, etc. So I want to maximize the probability. Now, this is also something that may be familiar if you've thought about data analysis at all or statistics. This is something that we also do when we're trying to fit data. We try to it's a maximum likelihood estimation, and so this is a natural thing we can do. Now it gets a bit unwieldy